Hi, I am Mark Leach. I am the developer of the Chemogenesis analysis and I'm the author of the Chemogenesis Webbook. In this video we're going to look at the periodic table and ask the question, is the periodic table perfect? Is the periodic table cracked in some way? Or is the periodic table actually broken? We're going to start off by looking at the perfect periodic table and various formulations and properties of the perfect periodic table, and then we're going to have a look at some places where the periodic table is not quite as simple or as obvious as we may think. The chemogenesis analysis starts with the periodic table of the elements. So we need to consider the periodic table in some detail. First we have the roots of chemical science. Here we're talking about the discovery of the chemical elements. Then we have the periodic table, and from this the chemogenesis analysis grows out of the periodic table to give us organic and inorganic reaction chemistry. So let's have a look at the periodic table. My personal favourite periodic table is the Web Elements website, which contains a vast amount of information about the chemical elements and their compounds. The Web Elements periodic table can either be seen in the common 18-column periodic table, or it can be expanded into the 32-column periodic table. I am a particular advocate of the 32-column form. Here we can see the 32-column periodic table as the element symbols, and here with the element numbers. So the question is, how do we get to the periodic table? Well, the answer comes from quantum numbers. So let's have a look how the quantum numbers are organised. We have four quantum numbers: the principal quantum number, the azimuthal quantum number, the angular momentum quantum number, which gives rise to the shapes of the sp and d orbitals, the magnetic quantum number, and the spin quantum number. An orbital can contain a maximum of 2 electrons of opposite spin. We can see the build-up of these quantum numbers in a table. So when n equals 1, there's just the s orbital. When n equals 2, we have s and p orbitals. When n equals 3, we have s, p and d orbitals. When n equals 4, s, p, d and f, etc. But if we look down, we see that there are quite a number of unknown elements. So how does this arise? Well, in neutral atoms, the approximate order in which subshells are filled is given by the n plus L rule, also known as Madelung's rule. So we can see the orbitals fill 1s, 2s, 2p, 3s, 3p, and another diagram showing essentially the same thing. So we can now look at the filling of the atomic orbitals: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine and krypton, etc. Slightly confusingly, we need to turn this upside down to actually see how the orbitals are filled. So now we have a diagram of elements by orbital, and we can see how the electron shells, subshells and orbitals fill up. Many scientists are big fans of the Janet or left step periodic table, as this shows how the orbitals fill in a rather elegant way. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d and 7p. So let's compare the Janet left step with the 32-column long-form periodic table. So on the top of the diagram we can see the orbitals filling, and the bottom we can see the representations of the two periodic tables. And here we have the 32-column long-form periodic table with the orbitals shown. Quantum mechanics gives us the shapes of the orbitals, and these can be visualized. Okay, variations on a theme. Ho ho, there are many variations on a theme. I'm the curator of the Internet database of periodic tables, and there are several hundred formulations on the database. The few given here are merely to illustrate the variety. Many regard the first periodic table as being the Telluric Helix from 1862. Mendeleev's very first representation from 1869. In 1898 we have Crookes' three-dimensional representation, various spirals. From about 15 years ago we have the Valery Zimmermann periodic table, and this can be converted into a rather splendid cube. Benfey has a spiral periodic table, the periodic table snail, and the Alexander arrangement is a well-known three-dimensional representation. We have a step pyramid, circular periodic tables, the Stowe representation, a rather nice three-dimensional one. We have the Dufour's periodic tree. Jeff Moran has produced a periodic spiral periodic table using hexagonal elements. So the question is, why do we use the conventional periodic table in either its 18 or 32 column forms, the Seaborg periodic table, rather than the Janet left step or any of the numerous other periodic tables out there? One word: periodicity. Repeating trends in element properties. These are only shown in the conventional periodic table, where there is a general trend bottom left to top right. Okay, so let's have a look at some properties of the long form periodic table. So first we have atomic mass and atomic number. Now this actually runs top left to bottom right, but most of the other properties, such as metallic properties, run bottom left to top right. All of the non-metals are found on the right hand side of the periodic table and higher up. First ionisation energy. Elements lower left have very low first ionisation energies. Elements top right have high first ionisation energies. Atomic radius. Elements bottom left are very large. Elements top right are small. Electronegativity. Electronegativity is a very important concept in chemistry. It relates many chemical properties into a single parameter. Elements bottom left are electropositive elements. Elements top right are electronegative. We can see these characteristics represented in this Wikipedia periodic table. Interestingly, we can take the bottom left, top right parameters and create an empirical periodic table. I personally like to use first ionisation energy. We have the data here. We can rotate this, remove some of the lines, clear up the points, squeeze the data together, and we can actually place this on a periodic table of the elements. This brings us to an interesting point about the position of hydrogen in the periodic table. Most periodic tables show hydrogen in group 1. This is because hydrogen commonly forms the H+ ion, the proton, and this is the agent of Bronsted acidity. Occasionally periodic tables show hydrogen in group 17. This is because hydrogen can form the hydride ion H-, which is similar to the fluoride ion, chloride ion and bromide ion. Some periodic tables show hydrogen above and between boron and carbon, because this is where electronegativity data shows where it should be, and some periodic tables show hydrogen floating in the middle. Okay, let's have a look at a typical bit of a periodic table showing the main group elements and have a look at some of the things that we can take from this. We can look at the number of valence electrons. These go 1, 2, 3, 4, 5, 6, 7, 8, and the group 18 elements are regarded as having a full shell of electrons. We have the valency. Valency goes 1, 2, 3, 4, 3, 2, 1. So the group 1 elements form +1 ions, group 2 elements +2, 13 elements +3, and at the other end, group 18 elements tend to be rather unreactive. Group 17 elements form the -1 ion, group 16 elements -2 ion, and in the middle, carbon, nitrogen, they tend to form covalent compounds. So we can use this data to ask questions such as, what is the formula of aluminium oxide? So aluminium is a group 13 element, it forms the +3 ion. Oxygen is a group 16 element, it forms the -2 oxide ion. So therefore cross multiply and we get aluminium oxide, Al2O3. Let's ask the question, is the periodic table fractured? So let's go back to the diagram with the periodic table tree metaphor, and we can see that actually at least 3 periodic tables. First, we have the periodic table of elements as basic substances. This is a philosophical idea. These are the idealized, the transcendental elements. In 1950 there were 97 elements, 2000 114 elements, in 2021 there are 118 elements. The last of these was actually discovered in 2010, tennessine, but it takes a few years for the discoveries to be confirmed and the elements named. So if we look at this data, in the year 2021 the periodic table is complete with its 118 elements. Now, what happens if later this year or next year we discover a 119th element? This has the symbol UUE, and this will be the first of the period 8 elements. The situation is not quite as bad with the Janet left step. The element 119 fits in quite naturally, as does element 120, but element 121, UBU, sits right out on the left hand side and is the first of the G block elements. Indeed, let's have a look at element discovery 1650 to 2020. Quite a number of elements were known before this, and we often say these elements were known to the ancients: copper, lead, gold, iron, silver, carbon, tin, etc. So if we plot this data, we can see that the elements were very slowly discovered until there was a sudden rush of discovery. From 1669 to 2010, 106 elements were discovered. That is 3.1 per decade. So are we at the end of an age of element discovery? The periodic table is complete with its 118 elements, surely. Now, the existence of an element is determined by the structure of the atomic nucleus, not by the electronic structure. If we compare the solar system to an atom, we can see that the nucleus is actually much smaller than the size of the Sun to the distance out to Pluto. The nucleus is tiny. Atomic nuclei are best represented using what is called a Segrè Chart, which shows the number of neutrons versus the number of protons. This chart shows all of the isotopes. A few years ago, it was common to talk about the possibility of an island of stability of super heavy nuclei, but I've not heard very much about this recently. Indeed, the most recently discovered elements, 104 to 118, have very short lifetimes. Now, it would be a remarkable scientific coincidence if the sequence of atomic structures finished at exactly the same place at 118 elements that the periodic table was also so aesthetically complete. And scientists hate coincidences. So now let's have a look at the periodic table of atoms in the gas phase. This is the simplest possible state that atoms can exist in. Obviously the group 18 elements, the noble gases, exist in this state naturally. Other elements have to be induced into this state. This is the state of atoms from which we determine first ionisation energies. Professor Eric Sherry of UCLA hosted a recent workshop looking at 3D and 4s orbitals. And he looked in some detail at the electronic structure of the scandium plus ion. Earlier on, we showed scandium with the 4s2 3d1 structure. And this would make one think that the scandium plus ion in the gas phase is going to be 4s2 3d0. But, as T.H. Huxley observed nearly 100 years ago, the great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact, spectroscopy actually shows the electronic structure of the scandium plus ion is actually 3d1 4s1. The d orbital is of a lower energy than the s orbital. Professor Sherry published a paper a few years ago looking at the energies, and we can see from this diagram 4s and 3d orbitals actually cross. So if we look at potassium, calcium and scandium, we see with scandium the 3d orbital is actually of a lower energy than the 4s orbital. The literature shows the scandium 3 plus ion is 3d0 4s0, the scandium 2 plus ion is 3d1 4s0, the scandium ion is 3d1 4s1, and the gas phase atom is 3d1 4s2. So as we come down, we are adding electrons. As we go up, we are removing electrons. This explains the general observation that transition metals lose their 4s electrons before their 3d electrons. So titanium 2 plus is 3d2 4s0, Fe2 plus 3d6 4s0, etc. Professor Sherry also spent some time looking at gas phase chromium, which has the electronic structure 3d5 4s1 with 5 parallel spin 3d electrons. The question is, why does chromium have this anomalous electronic structure? It transpires that 19 elements have anomalous electronic structures, so it is hardly uncommon. There are various considerations: the orbital energy, electron repulsion, exchange terms, a slightly peculiar quantum mechanical property when we have identical electrons. The equation is n times n minus 1 divided by 2. Chromium has 5 3d electrons, so therefore there are 10 exchange terms. Exchange terms lower energy. Sometimes exchange terms will tip the balance into an alternative ground state configuration. Sometimes they will not. Every case has to be considered separately. There are also relativistic effects. As atoms get heavier, the electrons close to the nucleus travel faster and faster, and they start travelling close to the speed of light. Relativistic effects influence electronic structure of heavy atoms in the 6th row of the periodic table, and these effects increase dramatically in the 7th row. Some s and p orbitals are stabilised by relativistic effects, whereas others are destabilised, so that ground state configurations of heavy elements may differ from those of lighter elements in the same group. Professor Sherry also notes that there are 4 ways of presenting group 3 in the 16-column periodic table. First, we have the traditional form, scandium actinium, with the lanthanides cerium to lutetium. Secondly, we have the favoured form, which is scandium to lawrencium, with the lanthanides being lanthanum to ytterbium. Thirdly, we have a split D block form with the lanthanides being cerium to lutetium. And finally, we have a sitting on the fence form, which gives the lanthanides as lanthanum to lutetium. But unfortunately, this gives a 15-element F block. We prefer the second formulation, lanthanum to ytterbium, as this can be easily dropped out of the 32-column long-form periodic table. I strongly advise you to have a look at the workshop presented by Professor Sherry, links in the description below. So now we come to the periodic table of elements in their standard state. This is the elements at 25 degrees C1 atmosphere's pressure, formerly 298 Kelvin, 100 kilopascals. Elements present as gas, liquid and solid in this periodic table. They present as metals, metalloids and non-metals. And we can also view them as presenting as metallic materials, network covalent materials or molecular van der Waals materials. There's far more about this topic in the Chemogenesis Webbook, link in the description below. There's a problem with the name term oxygen and hydrogen, nitrogen, fluorine, chlorine, bromine and iodine. Sometimes this refers to the atom and sometimes it refers to the diatomic molecular substance. Oxygen, the atom, has the electronic structure He2s2 2p4 and an electronegativity of 3.44, but the boiling point of minus 138 degrees C refers to the diatomic molecule O2. And we can see this in many periodic tables where some of the data refers to oxygen, the atom, and some to oxygen, the diatomic molecule. There's also an issue with phosphorus. Here is a website from the Royal Society of Chemistry which shows data corresponding to white phosphorus and a clear diagram of the tetrahedral P4 molecule. But if we look at Wikipedia, we find some information. Phosphorus has several allotropes with strikingly diverse properties. The two most common are white phosphorus and red phosphorus, but black phosphorus is the least reactive allotrope and the thermodynamically stable form below 550 degrees C. Most authors and most reference sources regard white phosphorus as being the thermodynamically stable state of phosphorus under standard conditions, whereas black phosphorus is actually the thermodynamically most stable form. To be honest, I don't know how to resolve this issue. Now let's have a look at valency, where valency is the number of bonds an atom can form in a compound. Let's consider nitrogen, oxygen and fluorine, which have valencies of 3, 2 and 1. Nitrogen, fluorine and oxygen all form diatomic molecules, N2, O2 and F2, and these are commonly shown as nitrogen triple bond nitrogen, oxygen double bond oxygen and fluorine single bond fluorine. But if we pass liquid nitrogen, liquid oxygen and liquid fluorine through a strong magnet, something interesting happens. The liquid nitrogen passes straight through the poles of the magnet, whereas liquid oxygen is paramagnetic and is attracted to the poles. The experiment is actually far too difficult to do with liquid fluorine due to its toxicity, but we assume that the result will be the same as liquid nitrogen. So how do we explain this? Well, it transpires that oxygen does not have an oxygen double bond oxygen structure, but is a diradical. In its ground state, molecular oxygen is a triplet diradical, and this causes it to be paramagnetic and attracted to the poles of a strong magnet. We can see this with the molecular orbital diagrams of the N2, O2 and F2 molecules. O2 has the triplet diradical structure, whereas nitrogen and fluorine have more expected structures. Professor Eugen Schwartz says the two diradicals are strongly stabilised by static electron correlation corresponding to resonant configuration mixing. Roald Hoffmann et al. Have shown that the molecular orbital ground state configuration of O2 has 1s2, 2s2 cores and resonating sigma and pi structures. Binary compounds. Many of the elemental hydrides are common and well-known compounds with expected from valency structures. Water, methane, hydrogen H2, ammonia, hydrogen chloride, sodium hydride, etc. But if we look at the periodic table of binary compounds, we find that there's actually a hydride gap, and many of the transition metals actually do not form binary hydrides at all. The story continues with binary fluorides. Most of the chemical elements form binary fluorides with the expected stoichiometry, such as BF3CF4, but when we look further, we find there are some unexpected compounds as well. For example, chlorine forms ClF, ClF3 and ClF5. Let's have a look at the main group binary oxides. We find that many of the oxides have the expected stoichiometry, BeO, CO2, OF2, etc. But interestingly, phosphorus and sulfur do not form the expected oxide under standard conditions. When we look at the full set of oxides, we find that there are some decidedly unexpected compounds. Lithium, sodium and magnesium are able to form peroxides and even superoxides. Chlorine can form oxides in which the chlorine is in the +1 oxidation state, +4, mix +5 and 7, and the +7 oxidation state. When we look at the main group elements, we find that lithium carbide exists as Li2C2, which is lithium acetylide, not the stoichiometric Li4C. Boron carbide exists as B4C, not the expected B4C3. Lithium boride exists as Li2B3, Lib2, or the non-stoichiometric Lib, where B is 0.8 to 1, and not the stoichiometric Li3b. More examples: sodium potassium metals are fully miscible with each other, forming the liquid metal NaC. However, lithium is not miscible with either sodium or potassium, but it is miscible with aluminium. So, what is going on? We have a complete periodic table since 2010. Is this an historical artifact? We have anomalous structures of gas phase atoms and ions typified by the scandium plus ion. Transition metals that lose their 4s electrons before their 3d electrons. Liquid oxygen is attracted to the poles of a strong magnet, but neither liquid nitrogen or, we assume, liquid fluorine are. Many binary compounds do not have their predicted from valency structures. What is going on? Time to have a look at Madelung's rule again. In neutral atoms, the approximate order, what's that? The approximate order in which the subshells are filled is given by the N plus L rule. It transpires that this rule breaks down rather quickly. A recent review paper published in January 2021 states the following: a strong conviction has emerged in the chemical community, which has survived to the present day, that periodic trends in the upper part of the periodic system are valid in general. However, we now know that the lighter elements with smaller principal quantum numbers in their valence shell have well separated energy bands and well separated electron density shells in space that can easily be approximated by the non-relativistic approximation of quantum theory with negligible spin-orbit coupling. This no longer holds for heavier atoms. The chemistry of the elements is richer than being satisfactorily pictured in a table. The individuality of elements from the same similarity group is most pronounced at the top of the periodic table, where the number of valence orbitals is small and the orbital energies and radii form bands with gaps. At the bottom of the periodic table, these distinctions become washed out. That is due to both the non-relativistic increase of the density of states and different screening effects, and the relativistic orbital shifts and the splittings energy and radii wise. Right, is there a solution? One possible solution is to consider there as being 4 categories of elements. Category 1 elements are the common main group elements. They are biologically important, electronically simple, and that they're explainable in terms of Madelung's rule. They're also highly abundant in the Earth's crust. Indeed, iron is the only one of the common elements that is not one of the category 1 elements. These elements are also biologically important. More than 99.9% of the composition of the human body consists of these category 1 elements. It must always be remembered that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and iodine exist as the diatomic molecules in their standard state, and there's the issue that the term, say, oxygen may be referring to the atom or the diatomic molecule. Periodicity is generally observed, however higher oxidation state species are observed with group 15, specifically nitrogen, group 16, 17 and 18 elements, particularly down the groups. One interesting point with the category 1 elements is that compounds are generally colourless. There are, however, the notable exceptions of the F2, Cl2, Br2 and I2, which are coloured in their standard states. These are notable exceptions, but the colour is associated with the diatomic molecule. Organic and biological chemistry almost exclusively employ category 1 elements, mainly carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur, except as catalysts or chemical reagents during synthesis. It must always be remembered that the paramagnetic O2 molecule is a signal that the neoclassical descriptions of covalent bonding and structure are an illusion. Category 2 elements. These are common, culturally and technologically important, but they often do not have easily explainable electronic structures and or periodic properties. Each element should be considered as a unique entity. Madelung's rule must not be assumed. These elements often exhibit multiple oxidation states, enabling catalytic behaviour, and the compounds are often coloured. Many of these elements are important as trace elements in biological systems, iron in hemoglobin being the most obvious. Others, vanadium, chromium, manganese, cobalt, etc., are also found. Category 3 elements. Category 3 elements are less common, but they do have a multitude of very specific technological uses. For example, zirconium, thorium, uranium and plutonium are important in the nuclear industries. Tungsten is used for its high density and very high melting point, neodymium in magnets, etc. The +3 oxidation state is surprisingly common, and of course Madelung's rule must not be assumed. Category 4 elements. These are all intensely radioactive and are generally used in very specific and limited applications, and specialist handling is required. A couple of examples. The isotope technetium-99m is used as a medical tracer. But perhaps most surprisingly, tiny quantities of americium are found in domestic smoke detectors. So most of us have a small amount of man-made category 4 element in our house. So, is the periodic table perfect? Is the periodic table fractured in some way? Or is the periodic table broken? Well, obviously the periodic table is perfect in the sense that the same periodic table of the chemical elements exists over the universe, because we use the spectroscopy of the elements to study the stars and distant galaxies. So the periodic table is perfect. We may be at a very peculiar time in history where we have 118 elements, and so the Seaborg periodic table, the normal either 32 column or 16 column periodic table, appears to be complete. This may be an historical artifact, so that's not really an issue. But is the periodic table perfect? Well, yes. The thing that is not perfect is our simplistic models of how we study the atoms in the periodic table. Madelung's rule is beautiful for the first 15, 20 or so elements, but it then starts to break down. The element where we really see this first happening with is scandium, but it certainly occurs with all the later transition elements and the lanthanides and actinides. We cannot use simple rules for these. All sorts of strange quantum mechanical effects come into operation. We can solve mathematically the hydrogen atom with exquisite precision, because the hydrogen atom only has one electron, and that interacts with the atomic nucleus. But as we add more electrons to atoms, not only do we have to consider how the electrons interact with the nucleus, we also have to consider how the electrons interact with each other, and this becomes ever more complicated. So, the periodic table is perfect, yes, but it is a little more complicated than we may first have thought. Okay, thank you very much.